So welcome to the final video. In this video we're going to talk about the pH of salts, what happens when you throw a salt into water, the common ion effect as it relates to buffers, and some calculations of buffer solutions. Right. So the first question we're going to ask is, when I throw these salts, these three salts, into water, do they become acidic, basic, or neutral in water? So we have to think about each one of these salts breaking up into its ions. So sodium chloride will break up into sodium ion and chloride ion. And it's going into water. So we could think about water as being ionized, at least to some small extent, to H plus and hydroxide. Now we have to mix and match. The cation of the one will go with the anion of the other. The anion of one will go with the cation of the other. And draw what we actually get from that. So I'm going to get sodium hydroxide and HCl. So this is a strong base, and this is a strong acid. And if I combine the strong base and a strong acid together, I get neutral, right? If I do sodium hydroxide HCl titration, I'm going to wind up with a neutral solution. So when these get mixed together, this is going to be neutral. Okay, now let's look at the Kf is going to break up into potassium ions and fluoride ions. Now when I do this mixing and matching, potassium will max up with hydroxide, that'll be a strong base, and the fluoride will match up with the H+. Now that's a weak acid, so that means fluoride wants something from water. It wants that H+ from water, and what's going to happen is it's going to react with water to give me HF plus OH minus left over. So the fact that I actually generate OH minus from this means that this is going to be a basic solution. Right? Because fluoride ion wants something from water, it reacts to make the HF and give me hydroxide ion, which generates a basic solution. Okay, so zinc. I take my zinc nitrate. Zinc goes to zinc 2 plus 2 NO3 minus ions, and we're going to mix and match again. I'll have nitrate and H plus, which is going to be nitric acid, which is a strong acid, and I'm going to have zinc and hydroxide. Now that's a weak hydroxide, so that means it's not going to be completely dissociated. So what I'm going to get when this goes into water is I'm going to generate some zinc hydroxide. It's going to generate some H plus left over. That water, the hydroxide from the water is going to go to the zinc and bind tightly, not be completely dissociated, leaving some H plus floating around in solution. So this is going to be an acidic solution. Okay, so the common ion effect just means that I have some common ion associated with it. So in this example, I have HF solution that's 0.2 molar, and I want to calculate how much F minus I have, the fluoride ion, in 0.1 molar HCl. Now remember that HCl is a strong acid, so the HCl is completely broken up into H plus Cl minus. So that means my initial H plus ion concentration is not going to be 0. It's going to be that 0.1 molar. And again, I have that 0.2 molar HF. And I also have to remember that since I know the Ka, I can write the Ka expression, which would be for the reaction. And I think that's an important thing to write out. A lot of people lose sight of what this reaction is. So what it is HF aqueous plus H2O liquid is going to be in equilibrium with the H3O plus aqueous plus F minus. So this is my acid dissociation reaction, and this is the Ka that corresponds to that. And the Ka is 6.8 times 10 to the minus 4. Okay, so I have my initial concentrations here. I have my 0.2 molar HF, and I have my 0.1 molar acid, and at this time I don't have any ionized F minus. So now we're going to get some changes going on. So what I'm going to get is I'm going to lose some. I don't know how much. I'm calling it X. I'm going to gain some X, and I'm going to gain some F minus. So at equilibrium I'm going to have 0.20 minus X. And again, at first I'm going to use an approximation method, and I'm going to say that this is equal to 0.20. I'm going to have 0.10 plus X. And again, I'm going to do the approximation and say that that's 0.10. Remember, I always have to go back and check. And my fluoride ion concentration is going to be X. Okay, so popping those numbers into my Ka expression, I get 6.8 times 10 to the minus 4 equals 0.1 times X divided by 0.2, and solving for X gives me 1.4 times 10 to the minus 3. Now this X is my F minus concentration, looking at the table again, going back 2 slides. So it's 1.4 times 10 to the minus 3 molar in F minus. I could also calculate my acid concentration. I could see when I add this amount to the 0.1 that I started with, it doesn't really do anything. It stays at 0.1. Adding this amount to it is insignificant, and it doesn't change it. I could actually calculate the pH by taking the negative log of that acid concentration, and the pH is going to be 1.00. Okay, so a buffer in general is just a solution that is a combination of a weak acid and its weak conjugate base. So that weak acid-base conjugate pairs are what makes a buffer. One of the most important buffers you have is in your body, in your blood. The carbon dioxide, the pH of your blood is regulated by carbon dioxide. We make carbonic acid, and that weak acid within your body regulates the pH of your blood. Okay. So what a buffer does is it resists a change in pH. It's a combination of a weak acid and a weak base. So if I throw in a little bit of base, it's going to react with the weak acid. If I throw in a little bit of acid, it's going to react with the weak base. So it kind of stabilizes the pH. So you can see here with some reactions. So my buffer solution is going to be a mixture of HF and F minus. So I have a weak acid and its conjugate base, the F minus. If I throw in some hydroxide, it's going to react with the HF and generate more fluoride ion and consume some of my HF. If I were to throw in some acid instead, it's going to react with the F minus and generate some more HF and take away some of my F minus. And this is really the nature of the buffer, so it helps stabilize the pH of the solution. Okay, so again, with any of these reactions, any weak acid, I can write a Ka expression. That weak acid plus water is going to be in equilibrium with the hydronium ion and the A minus. This is my weak base. This is my weak acid. And I can write that Ka expression, which is the products over reactants. Remember, we exclude the water because it's a liquid. Okay, so you don't have to know how to derive this formula, but I'm going to derive one of the most important equations that simplifies all your buffer calculations. And it's so simple. I'm going to go through the derivation, yet I'm going to provide it for you on the exam. It'll be at the bottom of the page, so look for it for solving any buffer problems. Alright, so I'm going to rearrange this slightly. So I haven't really done much of anything. I've just separated out the acid from my equilibrium expression. I haven't really changed it from my Ka expression. So now I'm going to take the negative log of both sides. And remember, we can take the negative log of anything, and that's like the p of whatever we're doing. So if I take the negative log of the Ka, that's the pKa. Negative log of the H plus is the pH. And then I have this negative log of this expression of my conjugate base over my conjugate acid. So with that equation, if I rearrange it, I could say that the pH is equal to the pKa plus the log of this ratio of my base over my acid. And this is known as the Henderson-Hasselbalch equation. And it's a really important equation if any of you ever do any biology research and have to generate your own buffer. This is the equation you're going to use to do it. Okay, so what is the pH of a buffer that is 0.12 molar in lactic acid, and there's a structure of lactic acid for you, and 0.1 molar in sodium lactate, and the Ka for lactic acid is 1.4 times 10 to the minus 4. Okay, you could see that the pKa is 3.85, and I'm very close to my 3.77. So with the Henderson-Hasselbalch equation, the pH equals the pKa plus the log of the A minus over the HA. I pop in my value for the Ka, take the negative log of it, and I put in my ratio. My lactate ion was 0.1, my lactic acid is 0.12. When I take this ratio, do the division, and take the log of that number, I get minus 0.08, and my pKa is 3.85, and I wind up with, after doing the addition of those two numbers, 3.77. So you can see if you look at this Henderson-Hasselbalch equation, really this is the key for the stabilization. My pH is going to be somewhere close in the range of my pKa, right? So 3.85 is close to 3.77, right? So that's kind of where I'm going to be buffering. That's my range of the buffer. And here is where the key part, the change is going to be. That change is limited because of this logarithmic relationship of these two. So if I increase this a little bit and decrease this a little bit, when I take that ratio, the log is going to make that a relatively small number that I'm going to be adding or subtracting to my original pKa value, causing that stabilization. Okay. So again, like I said, that pH range is going to be the area that I'm going to buffer in. The best choice when I'm choosing what type of buffer system I want is I want my pKa to be very close to the desired pH that I want to buffer at. So here's a little problem I want you to work out on your own. I have a buffer solution of acetic acid, and you could look up the Ka of acetic acid. So I have acetic acid here, it's 0.3 molar, and it's also 0.3 molar in sodium acetate, so that's my buffer solution. If I add some hydroxide to it, this amount, it's going to change my value of acetic acid and my value of acetate, and I'll get a new pH of 4.80. What I'd like you to do is go in, use the Henderson-Hasselbalch equation, and prove to yourself that you get 4.8 on this. Again, if you were to add some acid, again, my acetic acid value is going to increase, my sodium acetate value will decrease, and the pH now becomes 4.68. So this is the last video. I hope you enjoyed them. I like making them. I'm not sure if any of you guys are actually watching them or not. So what I want you to do is kind of give me that little Hunger Games symbol, the two-finger raised hand in class. Don't say anything to anybody. I want you to prove to me that you've actually gotten to the end of the last video. So next time we're in class after you've watched this, I just want you to give me the cross your heart and the two fingers in the air. All right? Study hard. Watch all the videos. If you have any questions, I'll be available. Hopefully by Edmodo while I'm away for Wednesday and Thursday. All right. See you soon.